So we've learned about the octet rule, and it is a rule, not a law. It is a rule to help guide us, and a lot of Lewis structures obey this rule and give us depictions of the real molecule. But there are exceptions to the octet rule, and there are three major exceptions. There is an odd electron species. Well, if you've got a thing that exists with an odd number of electrons, you can't possibly make everybody feel like they have 8. That's an even number. So there's odd electrons. There's also incomplete octets. There are some molecules that exist where they have less than 8 valence electrons surrounding it. They're reactive species. They're looking to get more electrons, but they exist with an incomplete octet. This third one is a big exception. There's a lot of things that have an expanded octet. Now this would be in the world of inorganic chemistry. You won't see this in the world of organics. So those of you who just go on to organic chemistry, you won't see a lot of these expanded octet exceptions because carbon is not one of those elements that can undergo that exception. But let's look at them bit by bit. Let's start with the odd electron species. So you go through and you count up valence electrons, and when you count up valence electrons, you find that you have an odd number to work with. So both of these examples would apply. Nitrogen, getting some ink flowing here. Nitrogen with an oxygen. All right, nitrogen has 5 off the periodic table, and oxygen has 6. So that's 11 to work with. You can't possibly satisfy the octet rule with that. NO2 would be another example. NO2, now very often we think it's going to have a minus charge, and that will help give it an even number, but this thing actually does exist, NO2, as a molecule, not as an ion. So we'd have our nitrogen with its 5 valence electrons, and you would have 2 times 6, 12 more, for 17 electrons to work with. So what I typically do, if I come up with an odd number, if I would stop and say, was I supposed to be doing this for an ion? Does it have a negative charge? And be looking for that. But if it doesn't have that, and it really does have an odd number of electrons, then I have to worry about how to give that the right Lewis structure. Okay, so here is actually the Lewis structure of the NO that I have there depicted on the screen. It is the closest I can get to giving everybody 8. We have nitrogen with 7 and oxygen with 8. The interesting thing about that one, and let's go ahead and draw it, is even though the nitrogen has an odd number, and the reason I would choose this one and not giving this one the satisfaction and this an oxygen having the incomplete, is because of formal charges, all right? Nitrogen has 5, and then if I do 1, 2, 3, 4, 5, this gives me actually a 0 formal charge on nitrogen. 1, 2, 3, 4, 5, 6. We do 6 off the periodic table minus those 6. This gives me the 0 formal charges, whereas this guy would be 5 minus 1, 2, 3, 4, 5, 6, a -1 formal charge, can't write negative that way, -1 formal charge on this nitrogen, and 6 minus 1, 2, 3, 4, 5, a +1 on this. So those aren't as good as formal charges. But when I have this, I have excellent formal charges. I just have a situation where I have an odd number of electrons. Okay, these things are called free radicals, and so free radicals are talked a lot about when you're talking about nutrition and trying to have a healthy diet, as well as the ozone layer, talking about free radicals and their damaging particles. They're looking for another electron. This is a very reactive species, and it's going to scarf an electron wherever you can find an electron. So it can cause a lot of chemical reactions to take place around it. The next one is an incomplete octet, okay? So an incomplete octet is when something has less than 8 valence electrons. So in a way, this is an incomplete octet, but that's not where I would categorize it. When you have an odd number, stick it in the odd category. But you have some species that have a situation where the central atom has less than 8 valence electrons. So here's some common examples. While this is beryllium, and beryllium is a metal and hydrogen is a nonmetal, their electronegativities are not different enough to call this an ionic compound. It is got those numbers, those electronegativity numbers, in such a way that they are actually sharing those electrons. So when we look at beryllium on the periodic table, it's in the 2A family, so it only has 2 valence electrons. And then each hydrogen has 1, so that's 4 to bring to the mix. And you're putting 4 electrons in, you can't possibly make anybody feel like they have 8. And so we've got a situation where it is got an incomplete octet. That beryllium only has 4 valence electrons. The other biggie, and that we're going to spend some time on, is boron when it has 3 things connected to it. Now, the electron configuration of boron you see there, 1s2, 2s2, 2p1. It only has 3 valence electrons. And those 3 valence electrons would like to share and make a bond. But we didn't really worry about where do the electrons start and where are they going to share when we did Lewis structures. And so we're going to see that boron, when it has 3 things connected, is going to be a common example of an incomplete octet. So I'm going to start by drawing a Lewis structure for it. Boron is in the middle, and the 3 fluorines surround it. Let me draw a line here so we can separate this from the work above. All right, so we have to count up our valence electrons. Boron has 3 valence electrons. Each fluorine has 7. That's from the periodic table. 7 times 3 is 21. So I have 24 electrons to work with. So I give everybody a single bond. Okay, and then I start going to the outside atoms. I'm using up to 24. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Everybody has 24. Now what we have been trained to look for when we're doing Lewis structures is if we have an incomplete octet for a central atom, we shift. And there could be shifting here, or here, or here. That would give us these resonance structures. And I'm going to go ahead and draw these resonance structures underneath it. So I've got boron with the 3 fluorines around it, with the electrons around that. But what I'm going to do over on this right-hand one is I'm going to shift these 2 that were sitting right here, and I'm going to make it a double bond. And I could put the double bond here, or here, or here. So let's go ahead and do all of those possibilities. So I have a boron with the 3 fluorines, and I want to put the double bond on this side in this case. Okay, and then I'm going to do the last possibility, which is to put the double bond at the top. Okay, so I have the double bond at the top. So this is what we were trained to do when we have an incomplete octet on the central atom, is we go ahead and shift and we come up with these resonance structures. So why does boron not do this? Why am I telling you that boron is going to be this instead? Well, if we do formal charges, it becomes evident. So let's do formal charges. Boron has 3 valence electrons. It has 1 per bond. That is going to give me a 0 formal charge on the boron. Fluorine, and each fluorine has a similar look, so it's the same thing. 7 off the periodic table, 1, 2, 3, 4, 5, 6, 7, and that's going to give me a 0 formal charge. So every atom here has 0 formal charges. Obviously, these are going to have different formal charges. Let's see what they are. We have boron, the 3 off the periodic table, 1 per bond, -4. We have a -1 formal charge. It's not too bad. We have a 0 formal charge for those 2 guys because they're looking like this guy. But this fluorine is really the culprit of why we can't do this. Fluorine has 7 valence electrons. We're going to subtract 1, 2, 3, 4, 5, 6. That gives me a +1 on the most electronegative atom on the periodic table. That is not going to happen. Let alone, I mean, this is great formal charges, so that's one driving force. But fluorine is just not going to share to that extent. Fluorine is not a good sharer. Fluorine is the biggest bully in the sandbox. He wants those electrons. He's not going to say, well, I'll just shift them on over here and I'll share with you. Not going to happen because of its electronegativity value. So while we can draw them, the formal charges make this a very unlikely contributor to the Lewis structures. So this is the why. But it's good to remember that when you have boron with 3 things attached, it is going to be an incomplete octet. Okay, incomplete octet. I've left an M out of there, but you get the picture. An incomplete octet when you have that. So that's a hard one for students to remember for some reason. You know, it's easy for me to remember. My research as a graduate student was with boron chemistry. I got this one down. But you kind of just have to put a flag up that if I have boron with 3 things attached, while I can draw and obey the octet rule, it's not going to obey the octet rule. It is going to stay as an incomplete octet. All right, we're ready for the last one, and that is an expanded octet. So our third exception is the expanded octet, and this is a really, really common exception to the octet rule, and we're going to see the places at which it applies. Okay, so this is only going to be able to happen when you're in atoms that are in the second period or beyond, and this is why, I mean beyond the second period, I shouldn't say the second period and beyond, because it can't happen with the elements in the second period. Carbon is one of the elements in the second period, and it cannot do this. But if you're beyond that second period, then we can have an expanded octet. Why? Well, they have d orbitals that can get involved in the sharing of electrons, and that d orbital participation can expand you beyond the just the s's and p's, which gets you up to the 4. All right, so that is what that's saying. When you're in the third period, you've got those d orbitals that are available to hold those extra electrons and get you beyond the 8. So when we are doing the octet rule being satisfied, we're getting the s and the p shells completely filled up. Going to the d's and starting putting electrons in the d is what allows us to get beyond the 8. So we're going to do several examples of this, okay? First of all, how do you know you're going to have one? Okay, you've gone through and you've given everybody a single bond. You're following the rules beautifully. You gave everybody single bonds. You went to the terminal atoms. You gave everybody 8. You still had more electrons to work with. You went to the inside electrons. You start giving them 8. Now everybody has 8. And you look at how many you were supposed to be using, and voila, there's still more electrons to be done. What are you going to do with those extra electrons? When you still have electrons left over, they have to go somewhere. And so at this point, they're going to have to go on the central atom and go beyond 8. If the central atom, if they're going to go anywhere, it's going to be on the central atom, and that central atom has to be in the third period or beyond on the periodic table, or it can't happen. So there are some times that you can have an expanded octet, and it looks like, you know, this element is just right above it on the periodic table. It should do the exact same thing too, but it can't because it's in the second period. All right, so we're going to do these examples here. Let's start with the SF4. Let's go to 4. SF4. So we go and we think about connectivity. We have sulfur in the middle and the fluorines around. There's nothing about it yet that makes me think that it's going to have an expanded octet. I go and count valence electrons. I have 6 off the periodic table for the sulfur. I have 4 times each fluorine has 7. All right, so I have 7 times 4 is 28, plus those 6 is 34 to work with. Okay, so I have 34 electrons to work with. I start by giving single bonds to everybody, 2, 4, 6, 8. I've used 8 electrons, and I go to my terminal atoms, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I think I added wrong. 7. Hold on for just a second. 28 plus 6, no, that's 34. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, I feel good now. Now everybody has 8. 8 everywhere, but I've only used 32 electrons, and that's a problem. I've only used 32, so I've got to place the next 2 somewhere. They have to go on here, and they're going to go on the central atom. So now this sulfur has 10 electrons instead of the 8 that it had before. Now let's just examine that formal charge, okay? Sulfur has 6 off the periodic table. It has 1, 2, 3, 4, 5, 6. It has a formal charge of 0. That's a nice formal charge for that sulfur right there. So this is something that can happen. Now, we could not do the same thing for OF4. Oxygen is right above it on the periodic table. It would have the same number of electrons. We would start drawing the same thing, that if it could do it, it would have a 0 formal charge. But the problem is, oxygen cannot do it. It is in the second period. And if it's in the second period, it cannot do an expanded octet. So while you can conceivably think about it, and it would have 0 formal charges, it is unable to go beyond just filling up the S's and the P's for the oxygen. All right, let's do PF5. No, that's not a P. Now it is PF5. All right, so I've got my PF5, my P is in the middle, and if it is surrounded by 5, boy, I'm mentally tired, I guess, 5 fluorines, we know right off the bat that if this thing exists, that it has to be expanded octet, because there's no way I connect P to 5 fluorines and use only 8 electrons. But there's a connectivity. We're going to count up, all right? So phosphorus is in the 5A family, and so it's got 5 valence electrons. See if I can do a little math here better this time. 7 times the 5, that's 35, plus those 5 is 40 electrons to work with. So now I'm connect with a single bond, 2, 4, 6, 8, 10, and then give everybody 8. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So I've used 40 electrons. All the fluorines have their 8, and the terminal atoms will always obey the octet rule. If anybody's going to disobey the octet, it's going to be a central atom. So there we've got the P with 10 electrons around it, and it's an expanded octet. All right, now you're going to try one. You're going to do the XEF4 one. I want you to draw the Lewis structure of XEF2. I want you to look at the XE that's going to be in the middle. So you're going to have XE, you're going to have F, you're going to have F, you're going to connect them with bonds, and you're going to put lone pairs around them. What I want to know is how many lone pairs do you have around them. Now let's just talk about language for a minute. For this guy, I would say it has 1 lone pair. Okay, it's a pair. There's 1 pair there. Once you've drawn this thing, I want to know how many lone pairs do you have around that xenon. Okay, did you say that there were 3 pair? If you did, then that would be correct. If you did not, and you wonder how in the world do you come up with that answer, then you'll need to watch what I do next, okay? So I've got 2 electrons, oh wait, I better count up. I got each fluorine, 7 times 2, and that is 14, plus a xenon, which has 8 valence electrons. Now these noble gases that are in the groups below neon, we can't do this for neon, but we can expand the octet beyond 8 for these guys. So here we have 22 to work with, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This would be where we would think we should stop because that obeys the octet rule. But now we have to put 2 more in there. So that gives us 3 pair around that xenon. Xenon is expanding its octet beyond the 8. And this can happen with those noble gases when you react them with really highly electronegative atoms. Those electronegative atoms can share with these noble gases, and once they started discovering that they could do that, that's where they went from being called inert gases, unreactive gases, to noble. We'll stand apart, we won't mix with the commoners unless we really, on a rare occasion, we can do that. Okay, so that ends our lesson on the exceptions to the octet rule. What are the 3 exceptions? There's the odd number. If you count them up and you have an odd number of electrons, there's the incomplete octet, of which you're going to keep in mind that beryllium and boron are your common examples of that. And then there's expanded octet, of which there are lots and lots of examples, but you won't see that example happening when you're in elements in the second period. So carbon, oxygen, nitrogen cannot do that expanded octet.